Welcome everyone. So we'll continue our discussion on these formal methods for system verification course. So in the last class, I have introduced different way of verifications. One is theorem proving, another one is model checking, and the other one is equivalence checking. So we specifically taken examples, and I show that how do you model that particular verification problem into theorem proving or model checking or equivalence checking, right. So I am still not introduce all the theories and all, and today also I do not want to introduce all the theories, rather I try to give you the kind of brief idea or overview what is different kind of logic, right. So from now onwards we will moving towards this theorem proving things. In theorem proving, if you remember, I talked about that whatever your problem you need to model as a formula, right, and during modeling the formula you might need different kind of logic, right. So that is the topic of today's discussion, the spectrum of logic. You may need a specific kind of logic to model a particular formula, right. So it is not that everything is under one umbrella, it has different categories. So what I am going to do today is I am going to take this different kind of logic and I will try to elaborate them with examples. Okay. So to start with, you have different kind of logic, which is say proposition logic, first order logic with theories, and higher order logic, right. So why do we need different kind of logic? It is effectively if you go this way down this line, it is more expressive, right, expressive. It means you can model more complex thing, right. But if you go other direction, the problem, decision problem is easier, right. What I am trying to show that there may be some examples or cases which can be represented in first order logic, but cannot be done in proposition logic. So you have to take first order logic, right. Or there may be something which you need first order logic with theories, but cannot be done in first order logic, and so on. So if you go down the line from proposition logic to first order logic to first order logic theories, you have more expressive power, right. You can model more difficult problems, but the decision problem, whether the formula is satisfiable or not, is more difficult to prove if you go down the line, right. So that is why we need to know a different kind of logic, and then the suitable one which is need for my problem, I will pick that one, right. So if we can model my problem in proposition logic, why I am going to take higher order logic, right, because it is much easier to prove a formula whether it is satisfiable or not in proposition logic as compared to higher order logic. I think it makes sense, right. So this diagram actually clearly captures this. It is more expressive power, right. So it is kind of proposition logic is subset of first order logic. First order logic theory is basically a superset of first order logic, and so on, and higher order logic is superset of everything, right. So this is the kind of hierarchy. So what I am going to do today, I am going to take each of them initially, and I will take examples, right, and I will show that such things cannot, say I will start with some small example which can be modeled with proposition logic, then I will try to take example which cannot be done with proposition logic, through which I will introduce to a first order logic, and so on, right. So this is how I am going to continue today. Before going to that example, we will basically just to recap the decision problem. So you have effectively satisfiability and validity problem primarily. So let us define them first. So to define the problem, you have say a formula, right. It may be in proposition logic or it may be in first order logic. We need to know what is the interpretation of the formula. So once you try to interpret the formula, you need to choose a domain first. Okay. So for Boolean formula, the domain is 0, 1, right, true or false, right. So if say other formula, domain can be natural number, domain can be set of all possible human being, right, human names, domain can be all possible universe stars, right, it can be anything, right. So you have to pick the domain, and then you have to give meaning of each of the component of the formula, right. So in a proposition formula, we already discussed in the last class, it will only have the propositional variables, right. The variable can take 0 and 1, right. But if you consider other one which we will introduce shortly, you can have a function, it can have a predicate, and so on, right. So, you have to take a meaning of that function, you have to take a meaning of the predicate and so on. So, let us take a propositional formula, say this. So, let us say I have 3 variable x1, x2 and x3 and say for a and the domain is 0 1 and there is a interpretation under which x1 is say 1, x2 is 0 and x3 is 0. You can think about true false as well. So, under this interpretation I will evaluate this formula and you can see clearly that if x1 is 1, x2 is 0 and then x3 is 0, it is a odd of these 3, it will be 1, right. So, I will say that under this interpretation the formula is satisfiable, because for these values of x1, x2 and x3 the formula is evaluated to true, right. So, the satisfiability formula checking is this: given a formula f and you just say whether the formula is true under an interpretation I, right. So, you have to find out there exists an interpretation under which the formula is evaluates to true, okay. See, and that is given by this symbol, right. So, if it satisfied, I will say I satisfies f, and if the interpretation does not satisfy, I will say the interpretation does not satisfy f. So, given a formula, I have to identify the interpretation, and you can have many interpretation, right. I have to find out the one of the interpretation under which the formula becomes true, then I will say the formula is satisfiable. So, that is the satisfiability problem. Then the validity problem, it is basically given a formula is valid if it is satisfiable for all interpretation, right, which we write usually like this. That means, for all interpretation satisfies the formula, okay. So, all possible values. So, if it is a propositional formula and there are say 3 variables x1, x2, x3, say here it has 2 to the power 3, which is 8 possible values, and I have to check whether the formula is true for all such interpretations, right. So, if you take this formula, say this x1 or x2 or x3, so this formula is clearly not valid, right, because if there is an interpretation where x1 is 0, x2 is 0, x3 is 0. So, under this interpretation the formula is false, this does not satisfy f, right. So, that means there exists an interpretation under which the formula is not satisfiable, so it is not valid, okay. And there are subsequent definitions called contradiction. The formula is contradiction if it is not satisfiable, right. So, that means there does not exist any interpretation under which the formula is true. So, it basically false for all interpretation, okay. So, we just recap the decision problem. So, given a formula, I have to check either the satisfiability or validity of the formula, right. That is the problem we are solving with theorem proving, okay. So, now let us move to the propositional logic. So, propositional logic is the most simple version of the logic, and in which what is you have basically set of propositional variables, right, and you have Boolean connectives, right. So, you can have this x1, x2, x3 kind of Boolean variables, and connective can be and, or, not, implication, by implications and so on, right. You have this, and obviously you have to define the well formed formula, in the sense that you should not have a formula say x1 or x2 is a valid formula, but x1, x2 then or, this is not valid, right. This is a valid formula, this is not a valid formula, which is called WFF, well formed formula. You have all the rules. I am not introducing the rules today, right. We will talk about the rules later. I am just trying to introduce the propositional logic with examples, okay. So, now let us try to take an example in which you have a set of English statement, and I want to check whether these 3 statement is true together, okay. So, how can I model this English sentence or the logical statement in propositional logic? So, what you have here, I am saying that if x is a prime greater than 2, then x is odd, right. So, let us I have a English statement, and which is true, right. So, the prime numbers are always odd number, right, except the 2, So, if the number x is a prime greater than 2, it must be odd. This is the first statement. Then I have a English statement, it is I am saying if it is not the case that x is not a prime greater than 2, which is effectively you are saying that it is not the case that x is not greater than 2, that means is effectively you are saying that x is a prime greater than 2. Okay. So, but this is a logical statement, and then you are saying ki x is not odd, right. So, you have 3 statements. So, effectively you can see here that this is actually false, right, because you are saying that any prime number greater than 2 is odd, and you are saying that x is a prime number, but which is greater than 2, but you are saying that x is not odd. So, it is cannot be true together. But if I have to model this in propositional logic, how we will go ahead, right. So, what I will do is I have to identify part of the formula as a propositional variable, right. So, what I will do that x is a prime number greater than 2. Let us say this is basically my proposition A, a propositional variable or Boolean variable, which true means which actually means this, right, x is prime greater than 2. Okay. What does it mean? That if A means this and not A means not of this. Okay. And then say x is odd, this is another, I just take model this as a Boolean variable B. Okay. So, now let us check here. So, what I have done here, I say ki x is a prime greater than 2 is my A, right, and x is odd is my B propositional variable. So, now I can easily model this English sentence, right. That means if A implies B, right. So, that means A implies B. So, A implies B, now model this first English sentence, right. Now, here I am saying it is not the case that x is not prime greater than 2. So, that means not of A, which is modeling this part, right, x is not a prime greater than 2. My A is x is a prime greater than 2. So, it is a not of A, right, x is not a prime. So, if you remove this not here, it says x is a prime greater than 2, which is my A, right. And now I am saying x is not a prime greater than 2. So, it is not of x, and I am saying it is not the case, which means negation of negation, right, double negations, and I am saying ki x is not odd. So, my x is odd is B, x is odd is B, so it is also not B, right. So, what I have effectively, I have formula 1 which is A implies B, then you have formula 2 which is not of A, and formula 3 is not of B. So, now I have to check whether these 3 together is satisfiable or not. So, you have to find out one possible value of A and B such that this formula is true, evaluates to true. Okay. So, we have already discussed that this particular case this formula is not satisfiable, right, but how do you check that? Something I will just give you the brief idea, how do you prove such scenarios. Okay. So, you can have 2 different way of proving whether a formula is satisfiable or not. One is called proof by deduction, okay, and the other one is called proof by enumeration. So, let me just talk about the proof by enumeration first. Enumeration is something you identify all possible values of the variables and just evaluate. Okay. It is kind of the truth table, right, which you have learned in digital design, right. So, that means in my previous formula I have A and B. So, I will just check whether 4 scenarios 0 0, this is my A, this is B, 0 1 1 0 1 1, and I have the formula which is this F1, F2 and F3, whether this is become true under 0 0, 0 1 and 1 1, right. So, I will just see if in some scenario if this become 1, that means this is satisfiable. I have to find out one possible scenario where the value become 1, right. So, that is called proof by enumeration, but you can understand that proof by enumeration is not a good solution. You have to basically keep checking, and there are 2 to the power n possibilities, right. So, it will take lot of time. So, in the proof by deduction, what we do, we have already some inference rules, right. which is true all the time in a proposition logic, let us say in proposition logic. And then I am going to use these rules iteratively on this particular formula and try to see whether the formula becomes true or false. Okay. For example, let us say the rules are very obvious, right. So, for example, contradiction. If your some formula q and not q, you have both there, right, it cannot happen, right. So, if you have say a and not a, it will be always false, right. So, that is it says that. So, this is basically called antecedent and this is called consequent. So, here I am saying that if you have a formula q and you have a not of q and both are true, right, whatever I am talking in the of is basically both are true and then it is basically false, right. So, this cannot happen together, that is called contradiction. And double negation is that if you have negation of q, that means q is also true, right. And this is called modus ponens. It is saying that if you have q1 implies q2 and you have q1, then q2 is also true. If q1 implies q2 is true and q1 is true, it implies q2 is also true. So, if you know the rules of implication, say a, b and a implies b 0 0 0 1 1 0 1 1, right. So, this case is this is false. Whenever this is true, this must be true, right. So, this is true and whenever this is false, I do not know, right. So, this is also true. So, what is saying that if this is true, q1 is true, so that means it coming under these two scenarios, right. So, this is true, q1 is true and q1 implies q2 also true, that means this is the only possible scenario is this cannot happen, right, because you are saying q1 implies q2 true, that means this is the scenario and then q1 is true. So, under these two scenarios, so this is the only scenario. Here obviously it means q2 is also true, right. Now, I have only these three rules, I can easily prove that this formula is not satisfiable. Okay. Let us see how we can do that. So, initially I have a implies b, right. You also have not of a, right. This is my formula 2, right. This is my formula 1, this is formula 2. So, from this I will get a by double negation rule. And now, I have a is true and a implies b is true, right. What does it mean? B is true by modus ponens, right, the rule 3. And now, you have formula 3 where you say not of b true. Now, you can apply the contradiction, right, a this b and not b, which is basically false. That means, this formula is false, right. This is how I can take a formula, apply this rule iteratively and I will see the formula is basically false. Okay. So far what we have seen, we have taken a small example and I have shown how we can model that with proposition logic and then I also discuss how to effectively solve that problem. But believe me, we will talk about all these things in large detail in subsequent classes. Now, we will try to introduce you to the first order logic. In first order logic, what you have the proposition logic and you also have the predicate constant and function. So, what is predicate constant and function is effectively you have in high level, we will formalize them much later. So, you can have a function like say predicate which can take some domain and it can map to true or false, or you can have a function f(x), right, which will take some domain to another domain, right. So, function map a element of a domain to another domain and predicate is effectively from any domain to true and false. It is a kind of a Boolean function you can talk about, right. And this domain can be anything, it can be set of natural number, set of real number, set of human being, right, human names and so on. So, in first order logic you also have these things and you also have the quantifier. Okay. That means, you have for all there exist, this is called for all, this is called exist. Okay. So, that means this is more powerful, right, that is what I am trying to show, right, that first order logic is more powerful than proposition logic because you also have these things. Okay. Now, let us take an example. So, just before giving this example, you can have predicate like this Hx, that means Hx is true means x is a human, right. Mx, that means x is mortal, right. So, if x is immortal, then it will be false, right. And say if x is not human, it some animal, other animal, then h of x will be false, and h of x is true means x is human, just to give some predicate. So, these are the kind of Boolean functions or predicate. Okay. So, now you have these things in addition to the proposition variable. You try to notice the differences. Earlier you only have the Boolean variable x1, x2, x3 and their connections, Boolean connections. Now you have this, plus you also have this predicate, functions and this for all that exist, right, quantifiers. This is called quantifiers. Okay. With this, let us take another example and try to model it. Let us say I have now 3 statements. Previously I talked about this prime number example. Now let us have, say I have 3 statements, say human are mortals, right. Mono is human and mono is mortal. Let us say I have these 3 statements. Again I have to prove that whether this F1 and F2 and F3 is satisfiable. So, I will not talk about how to solve this, but let us first encode it. Okay. So, I have already give you the example of this Hx and Mx in the previous slide, right. So, now I can use that. So, I can say that for all x, if Hx, that means if Hx is a human, implies Mx, right. It means that for all x, if x is human, then he is also mortal. So, this model this sentence, right, that humans are mortal, all humans are mortal, right. So, now you can see that this cannot be modeled as only proposition variables, right. You cannot just say ki I can take this x is the entire sentence, but then how do you model this? Mono is human, right. So, you are not able to logically model things using just propositional variable, right. So, or say you can, for argument you can say that, oh, I will tell this as y, this is z, then I will say x and y and z, but there is no connections, right. You can see the connections between these 3 formula, that humans are mortal. So, you are generalizing for all humans are mortal, and you are saying ki one human being named Monu, he is human. So, Monu is also mortal, right. But if you just model like 3 different propositional variable, that does not capture the relation between these statements, right. So, that clearly shows that this propositional logic is not sufficient to model this kind of English sentences or this kind of problems. Okay. Now, but with this first order logic, when you have these predicates and the quantifiers, you can do this, right. So, I have already shown you that how do you model humans are mortal. So, I have take 2 predicate Hx and Mx. Hx means equal to true, means x is human, and this is true means x is mortal, right, and false otherwise. With this I have modeled this, and then Mono is human, I can just write h of Mono, right. So, h of Mono is true effectively, and m of Mono, Mono is mortal, right. So, now I can just check whether f1 and f2 and f3 it is true or not. To proving that, again the deduction rule that I talked about here, like this contradiction, double negation, modus ponens, may not be sufficient, right. We need some other deduction rules, which is basically true for first order logic, and if I apply them iteratively, I can show that this is actually true or valid thing, because it is satisfying all, right. So, these cases the all the 3 statements are consistent and which is true, but other cases the statements are not consistent to each other, right. Okay. So, I hope you see the difference between first order logic and propositional logic. Okay. Let me take go to the next one, the first order logic with theories. So, this theories is a generic term. You can have different kind of theories. Okay. You can have this equality, you can have linear arithmetic, you can have bit vector, you can have arrays, pointers and everything. Okay. Theories is nothing but you are adding more power. Okay. Let me take one more example for this first order logic with theories. Let us say I want to model the statement. This is not to prove something, I just try to encode. Okay. There are arbitrary large prime number, right. So, you can have very large prime number. Okay. So, this I want to encode in first order logic with theories. So, I will show that you need something else to model this one, right. Just with first order logic you cannot model this. Okay. So, how do you interpret this line effectively? So, it basically says that for a prime number there always exists a larger prime number that is also prime. That is why this is arbitrarily large. That means, if you say this is the biggest prime number, I will say so no, there is another prime number which is greater than this. Okay. Then you will say, oh, this is the biggest one, no, I will find another one which is larger than this. Okay. So, this way it is basically encode the arbitrary large things in logic. Okay. So, here is the encoding. So, I will explain what I have written here. I have written here the for all x there exists p such that p greater than x. So, these are all first order logic, right, because quantified is there, Boolean propositional variables are there, and then this p greater than x you can actually think about a predicate, right, p x y, right. So, you can say that it is true if x greater than y, or it is false if it is otherwise, right. So, this is also kind of predicate. Okay. So, I am saying that for all x there exists an p such that p greater than x, that means p is larger than x, and for all v1 and for all v2. So, you take all possible value of v1 and v2 such that v1 is greater than 1, v2 is greater than 2, right. Again this is can be used this p v1 1 and this is p v2 1. I can encode this right. So, maybe I will just write that one after this. So, till that everything is first order logic implies p not equal to v1 dot v2, which is multiplication. So, this is where the theories come, the not equal to, right. So, not equal to or equal to, right, or say this multiplications, these are all in theories. Okay. So, so this effectively encode your this formula. I will explain the encoding. What I have done here is for every x there exists a p such that p greater than x. Okay. And for all v1 and all v2, v1 and v2 greater than 1. Okay. So, this is 1 actually implies p1 not equal to v1 dot v2. So, this is means what? This is the prime property. What is prime number? It is only divisible by 1 and that number. So, that means there does not exist another 2 number. If you multiply you will get p. So, effectively this says that p is prime, p is prime, right. So, you are saying that for all possible value of v1 and v2, if you multiply them it is not equal to p1 p2. So, that means p1 is not divisible by other than 1 and that number. Okay. So, this part is basically talking about p is a prime number, nothing else, and this part is saying that the arbitrary one, right, arbitrary large. Why? I am saying that for all x there exists p. So, if you take any number p is greater than that and p is prime, right. So, which effectively if you combine the entire thing it says that p is there are arbitrary large prime number, because if you take any big number, any possible value of x, there will be another P which is greater than this and P is prime, right. So, this basically a good example how do you model a complex statement logically using theories or the logic, right, and you need this kind of thing which is basically the theory. Okay. So, here you have more examples. So, the equality is different. So, you have equalities, you also have this linear arithmetic where you have plus minus, right. You can also have bit vector where you basically have this bitwise operations, right. This is right shift, A is right shifted by 2, right, and then you also have the array, you can have arrays, right, you can also have pointers. So, these are all theories, different kind of theories, and combined means it is everything. So, again I have already shown you a glimpse how do you show a formula is satisfiable or not in propositional logic. You can have similar kind of thing for first order logic, and similarly for different theories, right, equality, linear arithmetic, bit vector, you will have different rules, right. So, unless you need say arrays, I am not going to introduce the rules for arrays, I will keep it simple, right. So, in the theory also different subclasses are there as it is shown here. Okay. So, I think you can see the difference between propositional logic, first order logic and then first order logic with theories. You are adding more expressive powers. Okay. Now, I will move on to the higher order logic, in which it is basically you have the first order logic and you also have this predicate variables and predicate function variable. I will talk about that, the difference between constant. If you see here, if you go to the first order logic definitions, I have written here predicate constant, function constant effectively. Okay. So, it means that there is a fixed meaning of this constant, okay, and variable means they can be anything. That means they can be any kind of predicate, any kind of functions. Okay. So, that means here the functions and predicate are also quantifiable. Okay. Here I talked about only predicate constant and functions, and you can actually have proposition variable. Right. So, that is why I quantify here x, right. X is the kind of quantified variables in some domain, right. It can be Boolean or any other variables. I am not talking about say Boolean variable anymore. And in first order also the variable can be anything, it is not only Boolean. In propositional domain is only 0 1, right. But the difference here is that I am not quantifying the h or m, I am quantifying only the variables, the not the predicates. So, predicates are constant here. Okay. You have a fixed meaning of this predicate, but in the higher order logic you can actually quantify the predicate also. What I have written here, for all p, for all x, px or not px, right. So, I am quantifying the predicate as well. What is the difference? Here in the previous case you are saying that hx means human is mortal, it is a fixed meaning, right. Now, in this case p is quantified. So, that means you may have a predicate which means x greater than 0, right. So, predicate is true. You can have a predicate where you say ki x greater than 5, this can also be a predicate. You can say that predicate is means x is a human being, right. P of x, x is a dog, right. You can have different meaning of this predicate, right. Previous case hx has a fixed meaning, hx is true means x is a human being, but you can have different function or predicate. So, this formula is true means for all possible meaning of the predicate function the formula will be true, right. So, this is more powerful. Previously you are not, you are giving a single meaning of the functions or the predicates, now you are giving all possible meaning here, right. So, you are quantifying the predicate also. So, this formula may be true for when p is equal to hx equal to human, right, but it may be the case that for some other cases this is not true. Okay. But you can clearly see that it does not matter what is the predicate, you are taking Px and not Px. So, it does not matter what predicate it is, whether it is checking x greater than 0, x greater than 5, whether x is a human being, x is a dog, whatever it is, this will be always true, because you are taking the predicate and its negation, right. So, you can clearly see that this is more powerful than the first order logic, right. I will conclude with one more example with higher order logic. So, here I am taking a little bit complex formula, right. So, what I have written here, there exists a f. So, this is quantifying f such that f of a equal to b, and for all x Px implies Fx equal to g of x f of x, right. So, so g is nothing but a function which will take two values, right. One of the value is x, the other y is basically f of x, right, nothing else. So, this y is this, do not get confused by this. Okay. So, you are basically saying that for there exists a function f such that f of a equal to b, and for all x p of x implies f of x equal to g of x something, g of x y. Okay. So, this is you have. So, what are the things you have here? So, for as I mentioned, for propositional logic you think about an interpretation, right. Now, here also I will try to show you the interpretation of this formula. For propositional logic, your domain is always fixed, the Boolean domain 0 and 1, but here your domain can also be different. Okay. So, you will have some domain D, okay. But this domain can be set of integers, set of real number, set of maybe only or fractional number, right, set of prime numbers, it can be anything. So, domain can be different, even it can be all possible strings and so on. Okay. Then here as I mentioned, the f is only quantifying. So, you have to find out one possible meaning of f, right. If it is for all f, that means all possible function, right, you have to show that. Now, for all other things called free variables, right. So, you have basically free variables, free and quantified. So, quantified one I know I have to find out one function, okay. But for the free variable in interpretation, you have to assign some values, right. So, for example, for propositional cases I have assigned 0 or 1, but here if you have the function predicate, I have to give the meaning of that function. So, let us first see what you have here, right. So, you have the domain D, you have two free variables a and b from the domain. Let us say the sort of domain is integer, then I have to take some value, say maybe a equal to 5, b equal to 10 or something like this. So, I have to assign one value from this domain to these variables a and b. Then you have this function f of x, right. So, f of x is basically a unary function which is a domain to domain, right. That means, it will take say some value from this domain, let us say domain is the set of integer, then it will take say 5, it will map to some another value, right. So, maybe it is some function that map one value to the another value, and you can have many such functions, right. It can be unit function that it will always map x to x, it may be x to x plus 1, x to x square, right, all are different functions, right. And then you have g, which I have already talked about, it is a binary function, it will take two values from the domain and return another value in the domain, right. And then you have the unary predicate p, which is basically it will take a value from this domain and map to true and false, which is basically p equal to d to true false, right. The difference between function and predicate is basically it maps to true false, and here it maps to another element of the domain, right. So, unary means it have one argument, binary means it has two argument, this is f of x, right, this is g of x y. So, this may be mapped to x plus 1, this is one kind of function. So, if you give 1 it will be 2, if you give 2 it will be 3, right, and so on. The function can be f of equal to x square, say. So, if you are giving 1, output will be 1, if you give 2, output will be 4, if you give 3, output will be 9, and so on. So, you can have many such unary functions, right. And then if a binary function, it may be g of x y equals to x plus y. So, if you give z 1 1, output will be 2. If you are giving Z1 2, output will be 3. You are giving 2 2, it will be 4, and so on, right? Or it can be x minus 1, right? Then if you are giving x minus y, right? So if you are giving 1 1, output will be 0, G1 2 minus 1, Z2 1, output will be 1, and so on, right? So you can have many such binary functions. And similarly predicate, you can have many predicate that takes some value from this domain and map it to 0 1, right? But for an interpretation you have to give one, because they are free, there is no quantification on them, you just take one of the meaning, okay, and check whether the formula is true for that or not. It is actually have a meaning or not, the formula has a meaning or not, right. For many interpretation the formula may not have meaning, right, just like other case in proposition logic, for some assignment of value the formula may not be true, right, it may be false, okay. But you have to find out one interpretation under which the formula have a meaning here, right. So, I will give you an example for this formula and this is the interpretation under which the formula has a meaning, okay. So, let us say I take the set of natural number D, the domain I have defined, and let us say I have defined A equal to 0, B equal to 1, because I have to assign two values, I just assign 0 and 1, okay. You can assign many values, but I have to just take one. In under this interpretation, A equal to 0, B equal to 1. Let us say this f(x) I have defined as a predecessor function, x equal to x minus 1, right. So, if you give 5, it will return 4, if you give 3, it will return 2, and so on, and f0 equal to 1, okay. That is the definition of f(x), and say g is the product function, it will multiply. If it takes two input f(x) and y, it will multiply, okay. And then the predicate p is checking the greater than 0, right, this is p checking x greater than 0 or not. So, if you are giving px, you are just checking whether x greater than 0 or not. So, I have defined A, I have defined B, I have defined P, I have defined G, I have defined F. I do not have to define F and X because they are quantified. I have to show that for all possible value of X in this domain, in the set of a natural number, and F is for one function, okay. So, let us understand the meaning of this function here. So, what I am saying here, there exists a function such that there exists f such that f of 0 equal to 1, and for all x, if x greater than 0 implies f of x equal to g of x, and f g of f(x) is x minus 1, right. So, what is effectively, if I rewrite this, there exists f, right, such that f of 0 equal to 1, and for all x, if x greater than 0 implies f of x equal to x into f of x minus 1, because g is the multiplication, right. So, this is what I get. Now, let us understand what I have written here. There exists a function f of 0 equal to 1, okay, and for all other x, if x greater than 0, that means all x greater than 0, f(x) equal to x into f x minus 1. What is this function effectively? Factorial, right, factorial x. So, that means under this interpretation, this function has a, this formula has a meaning, right, which is basically captures your factorial number. So, if I ask you, you encode the factorial number computation function f(x) equal to x into f x minus 1, you have to write this formula, right. But if you have taken other interpretation, let us say f(x) equal to say successor function, this may be product function, when g may be addition function, this may be checking 0, the formula may not have any meaning, right. But under this interpretation, I just found out that this is clearly a factorial function which I capture. So, this is a valid interpretation or say a meaningful interpretation, right. The formula has a meaning under this interpretation, okay. So, I hope you understand the difference between these three different logic. I have not formally introduced those logic. What we will do in subsequent classes, we will take each logic at a time. I will precisely formally introduce their definitions, their syntax, semantics, and how we will basically check the decision problem on that logic, right. Today I just try to do it little bit abstract manner. There may be little bit ambiguity in the statements because I have not formally talked here, but once I introduce them one by one, you will appreciate the exact difference between different logic. Till then, thank you.